It has started. It has begun. Yes, what's going on? 5D. 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 Let's 5D this thing. That sounds like something in hyperspace. 5D. Let me make sure I'm looking at the right thing. This is determine the output for the following inputs.
No, it's.
Wait, what page are you on?
332.
Oh, 5D. I'm sorry. How is this machine related to the one that's shown in figure 6.13? Okay, so 6.13. Where is 6.13? Sorry, I got to go find it here.
It's on the previous page.
I found it. Okay. Okay, so 6.13. I think that it's related. Let me double check. 1 0 0 1 1 0 1. No. Huh. So now I got to go back and forth here. So 6.13. Here, I'll pull it over and we can look together and enjoy. There we go. Okay, so here's 6.13. Is that right? Yeah, no?
I thought it was.
Yeah,
It's
so
on
if you go on to.
Table, not figure.
Oh, table. Okay. Yeah, what? What's wrong?
That's just, okay.
Where is table 6.1?
It was on like, I think it was on the same page as the question.
Yeah, it's just
It's like
at the bottom of the same. Yeah, so go down.
6.12. Oh, here we are. Ah, okay. Okay, so, that is really complicated, isn't it? So, how is this related? What in the world? Do they do the same thing? It's hard for me to see exactly what's happening here.
You know, maybe it would be better if we also, what it does.
Oh, the first one?
it delays.
It's gonna repeat. Okay, so if you give it 1 0 1
Yeah,
it's gonna go 0 1 0 1.
Except for it doesn't do the last one.
Yeah, well.
It's just the same thing as we did in class.
Yeah, we did this thing in class. Similar.
Oh, okay.
So how is this related? Does this thing do a unit delay as well? Or let's see. 0 0 0 1. Yeah, I'd have to actually write out this 6.13. Do we need to do that? I think we might.
It says figure 6.1. Wait, really?
Which one are we doing?
No way.
Everyone's
Like scroll up to
pointing me to the wrong thing. That's what I...
That's table 6.13. We have to scroll.
Figure 6.13. Well, that's so I was on the right place. You guys are pointing me in the wrong direction. Okay, so let's see what this one does. Let's just pick a string like, what would you say, 1 0 1 0? And so in the example, the problem 6, it would go 0 1 0 1. Except we're not left. And so let's see, this one for 1 0 1 0, you get 0. Let's see, and then 1 0. So here 1 0. Does it do the same thing or use the unit delay? Let's see, if you start with a 0. So this is the 0 spot, and this is the 1 spot?
Couldn't you combine state 1 and state 0?
I think maybe that's what it's saying.
Yeah, these are the same.
It has a reduced number of states.
Yeah, this is the same. It's doing the same thing. It's just, yeah, that's a good point. Very nice. Okay, so we've solved the problem. Welcome. Thanks for coming. We were all waiting for you. I guess now the recording is unnecessary. I'll keep it going though, just as a good practice. Okay, so I guess we solved that after floundering a bit. and trying to figure out which of the figures or tables we were referring to. Okay, onward. Anything else that we need to deal with?
Can we briefly go over 1B?
1B, let's look at 1B, sure. So 1B, construct a state diagram for a finite state machine that recognizes each string that ends in this. It says here overlapping is not permitted, whatever. And also has length 4k, which means it's a multiple of 4. So yeah, this one's not too bad. It's an easy one I can do once I get this booted up and get that on the picture here just a sec. Okay, there we go.
Yeah, actually, I have a question.
Okay, so what we're doing is we need to have strings of length. So length is a multiple of 4 and end in 4 zeros. So that's what we're looking for. So let's just get this out of the way right now. Let's start. S1, S2, S3. So 0, 0, 0, 0, 0, 0, 0. 1, 2. Okay, so this is at least, oh, sorry, not 1. I messed up. Let me erase that. So just to explain what I've done here is I'm just accounting for the string 0, 0, 0, 0. So that one would qualify. And so if you start here, you go 0, 0, 0, 0, 0, 0. And then you're like, here's the fourth 0. And so my output will be 1. The reason I'm going back to the beginning is because this says that you have to have a multiple of 4 in terms of the length of this string. So now what I'm going to have to do is I'm going to have to account for that multiple of 4. So this will take care of the whole looking for 0, 0, 0, 0 at the end of the string. I just realized I need this to be on top instead of on bottom. It's just a minor issue here. So this is 0, 1. So now let's deal with multiples of 4. So in order to account for multiples of 4, basically I need to go somewhere else down here and count the number of bits that we're going to encounter, and only go back here when I've hit a multiple of 4, so that I can begin the count again to keep track of the 0, 0. So I'm going to go down here. If I get a 1, of course I'm not going to, so this is S3, S4. And then if I get another 1 or a 0, I move on to S5. And then the same thing. I'm putting this parallel with the track that's going to give me the final bit there, just to, for a reason I'll show you in a minute. 1, 0, 0, 0. And then both of these, this is S6, go back here. Okay, so we're almost done, but let me just explain here. Is as I move across, sort of these states are counting the number of characters in my word. So at S0, just think of that as being, if you're here, you have a multiple of 4, maybe 0. And then if you're in this column, one of these, you have a multiple of 4 plus 1, so maybe 1 or 5 bits. If you're here, you have a multiple of 2 more than a multiple of 4, and here you have 3 more than a multiple of 4. So these are telling me how many bits I have, or how many characters. And so the only way for me to start, since I want a multiple of 4 and end in this, the only way I'm going to start my counting of zeros to see if I've successfully got an end with with 4 zeros is if I'm back here. So any other situation, I'm just keeping track of the number of characters. There's a few minor things we have to deal with, and that is if I'm starting my count, let's say I begin with a 0, I'm like, hey, I'm over here. And then I get another 0, hey, I'm over here. But then I get a 1. Well, I still need to keep track of how many bits I'm on, but it throws me off of this track of being, in the sort of the counting of the 4 zeros. And so if I'm an S2 and I get a 1, I need to keep track of the fact that I have a 1. Oops. So
if I would get 1 and 3 or followed by 4 zeros, that wouldn't count.
That's right. 1 followed by 4 zeros does not count. 0. And then the final thing is what happens if you're back here. 1, 0. Here. So many zeros. There's only one 1 as an output, and that's, so yeah, a 1 followed by 4 zeros. You start with the 1, you're down here, you're like, okay, I'm not in the running for having 4 zeros in a row. Now I just want to keep track of how many characters I have. So here's 1, 0, 0, 0 puts you back here, and then the next 0, it's like, oh, maybe this is it. So, and that's because of this little requirement there that you want to have a multiple of 4 as the length of the string. That was way complicated. I don't know if that could be simplified, but this is sort of a brute force, just get her done. And you might be able to simplify it some. Yes?
So like one notation question we have is rather than drawing 2 lines from one state to the other, could you draw 1 and then draw like 1 input and output on the top one?
Yeah, I was tempted to do that. And I think that we all understand what that would mean if you did that. That no matter what your input is, you're just going that way. So, yeah, I think that would be legal. I feel like I've seen that somewhere, but I don't know if it was in our book.
Okay.
So that's the only reason I didn't actually do it. But yeah, I'm happy with that. If you have anything like this in the future. Yeah, I mean, the main thing is to be able to communicate what's happening. If you put a single arrow here with 1 0 on the bottom, 0 0 on the top, I think we'd all understand what's happening. So, yeah, thanks for that suggestion. Other things, concerns, or maybe ways to simplify this, because you guys might have a better idea. That seems really complicated. You got 7 states there. All right. Well, if not, yeah, I don't see a way, at least not immediately. But one of the things we're going to do today is start relations, which are going to allow us to actually, eventually, not immediately, but eventually we're going to be able to take something like this and evaluate it to see if there's any way to compress it, make it simpler. So that'll come. It'll feel like we're going kind of far afield, but we'll come back to it. So other things on the homework before we go on to these relations? Actually, we have a quiz first. All right, so I was mentioning to some people early on when I first came in, they're like, oh, is that the quiz? And it's like, yeah, it is. So the quiz, because I went to the trouble of, let's see, do I have? Yeah, I edited both of these. But I neglected to print. So we'll just do these one at a time. So take a minute and you can jot this down just as an exercise, just to see if you, the whole thing with the quiz, it's 2 things. I know you've heard this from me before if you've had me, but just in case, I do the quizzes for 2 reasons. One is so that I can accumulate a bunch of questions to put on your exams. So exam questions are similar to quiz questions usually. And then secondly, to see if you know what you're doing and to let you know whether you know what you're doing, because you think you do and maybe you actually don't. So it's both of those. So try this out. We'll go over it and then we'll try the second one. And I guess you can have overlaps. This one is okay to have overlapping things. Like number 1 made a big deal about that. or keep one. Figure out. Yeah, give you another 30 seconds or so to try to polish off your machine, and then I'll show you what I have. So in case you haven't written anything. So some of you look like you're all set. Some of you are still writing, which is fine, I guess. But let's go ahead and see what I've got, and then you can complain or contrast it with what you've got. So hopefully I did this right. We're counting the instances of 0, 1, 0, 1. So let's just think about this for a sec. If you just had that string 0, 1, 0, 1, you'd go here with your 0, then you'd go here with your 1, then here with your 0, and then back here with your 1, and you'd have an output of 1. Now, in terms of the other things that we might encounter, if you begin with a 1, you're just going to sort of hang out here until you get a 0 so that you can sort of keep track. If you start with 2 zeros, that's okay, because we're not doing this whole number of, like, you don't care if there's a multiple of 4. But anyway, 0, 0, you can have as many zeros at the beginning as you want, but then once you get a 1 after a 0, then you're like, hey, this might be a 0, 1, 0, 1, and so on. If you have multiple 0, 1, 0, 1s in a row, this will count each one of them, even the overlapping. So if you have a total of 6 characters, 0, 1, 0, 1, 0, 1, you get 0, 1, 0, 1, and it spits out a 1 for that one. But then you have another 0 and a 1 spits out another 1 because those two are overlapping 0, 1, 0, 1s. Everything else I think I've got in the right place, but if you have critiques, I'm happy to hear it. For example, if you have 0, 1, 1, it spits you all the way back to the beginning because you need to restart, if you will, looking for your 0, 1, 0, 1 sequence. If you have 0, 1, 0, and then you have a 0, then it puts you back here because you've already got your 0 sort of set in place for the 0, 1, 0, 1. But so you don't have to go all the way to the beginning for that. So I think that's it. Is there other questions? You'll notice also just a couple other things and then see what questions. Each one of these has 2 arrows. So since there's 2 different inputs, possible inputs, you need to have 2 arrows emanating from each of, wait, there's 1, 2, and then 1, 2. So each state should have two arrows emanating from it. So you can double check that with your machine. So what about you? Do you have comments or questions or critiques? I'm happy to hear. What do you think, Peyton?
So why wouldn't you go back to the state 0 when you get a 1 at state 3?
State 3. Okay, so this is because.
So would it be okay, like if you had 0, 1? Oh, yeah.
So
Is that okay?
for this input, I see. Whoops, it's not going to work. There, that's going to work. So here's 1, 0, 1, 0, 1 sequence, and then here's the other one. So change colors. Let's do it like this. And I need to be able to count both of those. So if that's my input, my output, get the color that I can use. So this is input. The output ends up being 0, 0, 0, 1, 0, 1. And so here, there are two sequences. And if you went back to the beginning and started counting again, it wouldn't detect this second sequence. You wouldn't get a 1. So it's almost as if it's keeping track and saying, hey, I've got a 0, 1, 0, 1. And it goes back here to say, I'm already set up with the 0, 1 in this blue sequence. And the only reason I might go back to the very beginning is if now I get a 1, if things get messed up. Other comments, questions? Or do you have a different way of doing it? Did you have similar number of states, more, fewer? I don't think you can do this with fewer, but I'd be happy to hear if you have a solution. What do you think, Lucas?
So I'm just having trouble with like ending the machine.
Ending?
Like I had like a state 4
Uh-huh.
with 1 going over there,
Uh-huh.
and that was just the output. But that's not really achieving anything. So I don't know.
I mean, there's nothing really wrong with having a state 4. So this would be something like this. Whoops. We need to get rid of all of that. There we go. So let's just explore this just for a sec. So there's nothing wrong with that. But then you have to ask yourself, okay, you're going to have two arrows going away from state 4. Where do they go? And you just have to make sure you put them going to the right place. So if I had a state 4 like that, then I might do this. I'd say, okay, now if I get a subsequent 0, I'm going to go back to state 3 to sort of keep track of the fact that I've already got a 0, 1 in place. And then I go back to state 3 with my next character, which is a 0. And then the next one would give me another output of 1. So that's fine. And then, of course, you have to deal with what happens if you get a 1 in state 4. And I think that's going to put you all the way back here. Because if you get a 1 in state 4, it means you have two 1s in a row. So you have to restart looking for 0, 1, 0, 1. So yeah, it's fine to have more states. And I think, as I mentioned, eventually, probably next Monday, we'll actually use relations to take something like this and say, that S4, it's not necessary. And here's how we can shorten this whole thing. And other comments? I'm happy to look at whatever you got. All right, thanks. Yeah, because this is helpful to me because I'm not collecting this. It's helpful to hear about other ways of doing this. Sometimes I'll see something that someone's done and I'm like, oh, that's interesting. Nothing wrong with it. There's nothing wrong with this. Okay, let's go on to question 2. Question 2 is a little bit easier maybe, I don't know, is tell me in a single sentence, I don't want paragraphs, but I guess you can write a paragraph now because I'm not going to read it. So I'm trying to limit the number of whenever I give a quiz. So tell me what this language, this machine recognizes. So explore this for just a minute, and then tell me what this does basically. Okay, sorry it took me so long to write this. I realized it says single sentence. So I first wrote this as a regular expression, and then I wrote it as a single sentence. Well, actually, I didn't. I had a sentence fragment, so I had to make it into a sentence. But I have my sentence now. I'm not going to be checking your punctuation or your grammar, unless it's mathematical grammar. So, and I'm not even collecting this, so you could have written almost nothing, or you could have written nothing. Let's go ahead and take a look at this, though. Hopefully you see exactly what's happening is that you're sort of keeping track of the number of ones. Like the ones seem to be what's advancing us over to the right. So let's see, how many ones do I need to get over to that special place over there, S3? So we need 1, 2, I need 3 ones. Once I have 3 ones, I'm over here, and I stay over here forever. So it seems to me like I can have any number of zeros in any order. All I care about is the fact that I have 3 ones somewhere. And so in plain English, that just is this here. It recognizes strings with at least 3 ones, anywhere they are. And yeah, like I said, I did this first, and then I was like, oh, wait a minute, I got to do a sentence. So there's the regular expression. Notice any number of zeros then a 1, any number of zeros then a 1, any number of zeros then a 1, and then you're all done. But you could put any number of ones or zeros at the end. So comments, questions, was that pretty straightforward? Hopefully you could recognize exactly what's going on. Like I said, I'm not collecting, sadly, so I can't tell if you guys know, but hopefully you know, understand what's happening. We can parse something like this. So it'll be on the next test, which is it next week? Not this week. I think it's next week. I don't know. I have it on the syllabus. So whatever the syllabus says, so don't take my word for it. The syllabus. Okay, let me PowerPoint this thing. Where is my PowerPoint for today? Back to relations is today. So we're going back to relations. I say back because at some point in your past, supposedly, in elementary discrete math, you had relations. If not, it's okay, because we're basically going back to the beginning. So what is a relation? Well, here's a couple of examples. Relations are things that relate to things or to objects in a set. Why is that on? It's because I did not turn it off. Let's see, can I turn it on? Beautiful. So nice. So here's 2 examples. Greater than or equal to is a relation. And it's a relation on the set of numbers. So we could say something like this, that 3 is related to 2. So just so you know, the notation that we're going to use is we're going to use this R if we, now, generally, I mean, this is kind of silly. We're replacing one symbol with another symbol, which is kind of dumb because we all know what this means. So we're not really saving any space, or we're actually making things more confusing, aren't we, with that symbol. However, we don't have a symbol that represents this relation, has a class with. So up here, the universe that we're interested in might be numbers. Let's just say all real numbers. Whereas this universe might be all students at MPNU. And so we could do something like this, that Jack, whoops, why did that not stay? Jack is related to Jill. What that would mean is that Jack and Jill are in the same class. So let's see if we can identify some relationships. Here we have something like this, that Sarah is related to Pearson. I before E? Yep. Awesome. So at least it follows the rule. I before E, except after C, in weird words that are innumerable. But anyway, so Sarah is related to Pearson because Sarah and Pearson are in this class together. Now let's see if we can come up with a situation where Sarah is not related to someone. Let me think of someone that we know. Yeah, we got modern algebra to contend with, don't we? Okay, how about this? There's a new student, Cooper. We're gonna go with Cooper, freshman, just came in. So I don't think you're in any class with Cooper. Do you know any Coopers? You do know a Cooper. Are you in a class with him?
I am.
Darn. Okay.
Give me some other people.
Yeah, some other Cooper. We'll just pretend. Not in the same class. So just like here, up here at the top, we might say that 1 is not greater than or equal to 2. You could say that Sarah's not related to, okay, here, just a minute. I can make up a name. Just so that we have bar, gall, I don't even know if that's the right way to spell it. Probably not. Doesn't matter. I should have just written Bart. There's no Bart in your classes. No Barts. Good. Okay, so Sarah's not related to Bart or Bartholomew. However you spell his name. These days, you can spell it however you want, right? Sound it out. But anyway, so there it is. There's some relationships. So relationships on languages, just briefly I mentioned that we can think of a language as being a relation itself. So if you have a language, you could say, oh, look, all the words in this language are related to one another, and any word that's not in that language, not related to the words in the language. So relations can be thought of in terms of languages, and finite state machines, you can think of some relations there. If two finite state machines do the same thing, that is, they have the same output for the same input, then we might say that they're related to one another. So something like that, we can think of those. We'll come back to those, though, in a bit. For now, though, we're just going to do some basics. I don't know if you've already gone over this at some point in your career as a discrete mathematician, but we're going to do it now, just to be sure that we're all speaking the same language. So these are properties on relations. Modern algebra, I think, has this sort of language as well. So if you're in modern algebra, you might see these words at some point. Maybe you already have. I don't know, has the modern algebraists, have they done this? Professor Hewlett, has she done groups? No groups? Has she done anything?
Still proofs.
Oh, basic proofs. Okay, so basics, the basics. It's okay. No, it's good. It's good. You know, just to remind you that there are proofs. Oh, Lucas doesn't remember proofs.
We started modulus.
Yeah, modular arithmetic.
Yeah.
No, that's good stuff too. Yeah, it's good.
So I have a question with the greatest common divisor. That would be a relation, right?
Greatest common divisor is not a relation. Unless you think of it as, do these things, are they relatively prime? Relatively prime is a relation. Okay, let's go back here. Okay, this is good thing. So, oh no. Let's see what I do. How did I do that? Okay, so GCD is not a relation, it's a binary operation. Binary operation, is that what we call it? Anyway, so GCD of, say, whatever, 6 and 4 is 2, whatever. But if you want to have a relation, you could say that A is related to B means that the GCD of A and B is not 1. So that would be a relation. And that's an important relation when you're dealing with the size of groups or when you're dealing with certain things with modular arithmetic. You want the GCD to either be 1 or not 1 in order for things, certain things to work out. Is she doing Euclidean algorithm?
Yes.
Okay, that's fine. All right, I love Euclidean algorithm. Okay, but getting back here, reflexive, symmetric, anti-symmetric, and transitive are properties that we're going to talk about in regard to relations. And we can go back, and if we all understand what this means, let's see, that would mean that 6 is related to 4, but 6 is not related to 7. So if we're using this as a relation. Anyway, getting back here, reflexive. Reflexive is what it sounds like. I don't know if everyone did this morning, but I did. Maybe you can't tell, but I looked in a mirror. And in that mirror, I saw a reflection of myself. So reflexive just means that something, a relation is reflecting back the original. So here's reflexivity. This is the sort of a description, mathematical description, but I'll give you a better description that's easier to understand in just a minute. So all this says is that if you, for every member of the set that we're interested in, that thing is related to itself. So it should have been a capital R, but you get the gist. So reflexive just means that everything is related to itself. So this relation, greater than or equal to, is reflexive because everything is greater than or equal to every number. It's like 3 is greater than or equal to 3, 5 is greater than or equal to 5, and so on. This relation is not reflexive. By the way, this notation, let me explain really quickly what that notation means. That notation you can think of as a list or a set of all the different things that are related. So, for example, if you use this relation here, that relation just says that A over B is bigger than 2. So that means that 3 is related to 1 because 3 over 2 is greater, or 3 over 1 is greater than 2. 3 is not related to 2. I suppose we should specify our set here. We're interested in the integers. So that is the integers. You might wonder, why is that capital funny looking Z the symbol we use for integers? And it has to do with the fact that this is derived from German. German, they don't know how to spell, apparently, and they spell integers with a Z at the beginning. All the other words they got right, like real, they used to. Real looks like this. Imaginary, I guess you have this for rational, that's quotients. Or irrational, or rational numbers. Yeah, that I doesn't look right to me. C for complex. Let's see, what other symbols do we have from that? And the reason that they have that funny looking line there is because back in the olden days, like when I was a student, your age, we didn't have whiteboards, we had chalkboards. And so it was common for mathematicians to draw their symbols. So if you had a piece of chalk, I'll just illustrate with this, you would be writing with it, but then when we got to a symbol like this, you turn it on its side to, and then draw it so that it's sort of this bold face, that they would make with the chalk on its side. And you can imagine that when you did that, you'd end up with this line here, sort of thing. I remember lectures that I attended where they used the chalk and they did exactly this, and this is what it would look like. If you took a chalk, put it on its side, you draw a Z, you end up with that sort of shape, or it looks like that. But anyway, that's just a historic note as to why it is that we have those symbols that look like that. Okay, getting back to this. Let's see if we can identify some other things. Let's see, 5 is related to 2, but 4 is not related to 2 for this particular relation here. Let's pick a few more. Make up your own, and then I'll pick some people to tell me a few, just to get some different ones here. So pick 2 numbers that are related to one another, integers, that are related to one another in this particular relation. And we'll just go around. Joseph, do you have 2 numbers that fit this relation? All right, just pick a big number. I'll help you with this. Pick a big number, any number. 16 is good. Then pick another number where that is less than half of 16. 4 is good. So 16 is related to 4 because when you put 16 and 4 into this, 16 over 4 is greater than 2. Very nice. All right. Gina, do you have a pair of numbers?
Sure. 24 and 3.
Yeah, 3 works because 24 divided by 3, 24 over 3 is greater than 2. Perfect. A couple more, maybe. Pearson, what do you got?
62.
6 and 2, because 6 divided by 2 is greater than 2. Okay, Sarah, let's have one more.
8 and 2.
8 and 2. All right, very nice. So 8 divided by 2 is 4, which is greater than 2. Let me just point out, they don't have to end up with integers. For example, 5 over 2. 5 is related to 2 because 5 over 2, 2.5, is bigger than 2. Okay, so that I'm saying is not reflexive, and the reason is that no number is related to itself. Is 7 related to 7? No, it's not, because 7 over 7 is not greater than 2. So you have a relationship there, not reflexive. Let's go back to our relations that we already have here. Go back to this one. Greater than or equal to, I think we all can figure out that that is reflexive. What about has a class with? Is that reflexive? For example, if Jack is related to Jill, is Jill related to Jack? Yes? Why is that? How do you know for sure?
I mean, they have the class together.
Okay, yeah. That's exactly right. So if Jack is related to Jill, it means there's a class that he shares with Jill, and we can just go to that class and say, Jill, is Jack in your class? Yes, he is. So very good. I know, it's a ridiculous question, and you were right to think of it as ridiculous. Okay, so that has class with, good. What about, where's this other one, the GCD one? A is related to B as long as the GCD of A and B is not equal to 1. So is this is this reflexive? Oh, wait, I'm sorry. We were doing reflexive. Crap. Sorry. I was just doing symmetric with you. My bad.
I was gonna say.
Yeah. Okay, sorry. I was just, so I apologize. Got a little ahead of myself. That was the symmetric. We're going to the symmetric in a minute. Sorry. So has a class with. Let's back up. Has a class with, is it reflexive? So is Jack related to Jack? Does Jack have a class with Jack? As long as Jack is a student at MBNU, he must have at least one class, and so he has a class with himself. Each of you are in class with yourself right now. It's a little weird to think about, some sort of multiple personality situation, but that's the situation. Okay, now let's go back here. Let's see, is the GCD, so now we'll do this, is this reflexive? So is A related to A? What do you think? Yes? Why is that, John?
So long as A isn't 1.
Ooh, interesting. As long as A is not 1.
So this is not reflexive.
Not reflect. Okay, very good, very good. Good to point that out. I'd missed that in my haste. Thank you. So yeah, if A is related to A, because like 6 is related to 6 because the GCD of 6 and 6 is not 1. 12 is related to 12, etc. But 1 is not related to itself because the GCD. And I suppose if we include 0, 0 is not related to itself because the GCD of 0 and 0 is undefined.
But wouldn't it be related because it's not 1?
It doesn't have a GCD. Is it non-1?
Isn't
I guess it isn't 1. You're right. Why not? I guess it depends on how we're defining this. Okay, very good. So this is not reflexive. One bad apple. Thank you, John. One bad apple spoils the whole lot. So this is not reflexive. Okay, onward. How much time do we have? 9 minutes. That's all right. Symmetric. So we already mentioned symmetric, sort of. Symmetric just means that if Jack is related to Jill, then Jill is related to Jack. Let's not belabor this. I think we can figure this one out. So in terms of these ordered pairs, A, B is in this relation, means A is related to B. Well, if that's the case, then B is going to be related to A. Equality happens to be symmetric, but anything with a less than symbol is not symmetric. Is married to is symmetric, we would hope. I am married to Tanya, Tanya's married to me. So there's a relationship there that's, hopefully, yeah, I can't imagine it not being symmetric. But then likes, that is not symmetric. So I'm thinking of likes in a sort of romantic sense, the way that you guys are running around saying, oh, I like this girl, or I like this guy. Or it can be just in a more general, like, I like that person. And that person might be like, I don't like you. You know? So not symmetric. But certain relations could be antisymmetric. Antisymmetric means that if A is related to B, then B is not related to A. So less than or equal to are antisymmetric in the sense that if like 3 is less than 5, then 5 cannot be less than 3, those sorts of things. Now notice that this is only when A is not equal to B, so less than or equal to is also called an antisymmetric. So this would be less than or equal to works as well. So any relation where you can switch them. Okay, so let's move on just so that we can get on with this. Transitivity, modern algebraists will be using these words soon. But anyway, transitivity just means that if you have, like, if Jack is related to Jill and Jill is related to Bart, then Jack should be related to Bart. So you have this transitivity that goes on. It's intransitive if it's not transitive. So here's a couple of examples. So is an ancestor of, that's transitive. Because, let's see, we'll just do my grandmother Smith. She is an ancestor of my mother, and my mother is an ancestor of me, and so Grandma Smith is an ancestor of me. So you've got this transitivity there. Likes between people is not transitive because I could like you, and you could like your friend Chad, but for whatever reason, I don't like Chad. So that sort of thing, non-transitive. What about is located within 1 mile of? Think about that. Is that transitive? So right now, I am located within 1 mile of my wife, and my wife happens to be located within 1 mile of Dr. Fuller. So, and does this mean that for sure I'm located within 1 mile of Dr. Fuller? Oh, no? What? Wait a minute. We're all in the same circle, aren't we?
You're all standing in a line.
Ah, good point. Yeah. So I could be here, me, and then maybe 1 mile away, there's my wife. And there's 1 mile separating us. And then Dr. Fuller is over here. And there's another mile, but maybe just less than a mile. But look, I am definitely not within a mile of Dr. Fuller. Very good. All right, very nice. I know that's a silly example, but so I had some group work here, which we only have 3 minutes for. Let me see what's important. Let's see. So I want to know whether something is reflexive, symmetric, antisymmetric, or transitive. So you basically are making a chart, which one is which. And let's just do this one here. Let's see, this one here, and this one here, just to get a quick flavor. I know we only have 3 minutes, so we got 1 minute per. So try those 3. Identify if they're reflexive, symmetric, antisymmetric, or transitive. And I'm not telling you what the underlying set is, so just assume it's the characters here. So you only have 1s and 2s to work with here. Here you have 1s, 2s, and 3s. Here it's any integer, it looks like. So that's it. Okay, so let's just whip through this really quick. Reflexive. Is this one reflexive? So Joshua, what do you think? Is this reflexive? Reflexive means that everything is related to itself. 1's related to 1. We're good, right?
Yes, it would be.
What about 2? Is 2 related to itself?
Yes.
Is it? Wait, no, these are the only relationships in this thing. So is this, what's wrong? No, 2 is not related to itself here. You would have to actually explicitly have a 2, 2. Yeah?
Couldn't you do the transitive?
Well, that's assuming that this is transitive, which also this is not transitive. So I'm asking yes, no, is this reflexive? It's not reflexive because for it to be reflexive, I would have to have 1, 1 and 2, 2. 1 would be related to 1, 2 would be related to. What this is telling me is that for whatever reason, 2 is not related to 2. It's not on the list here. So not reflexive. So reflexive, no. What about symmetric? Symmetric means that if you have a relation here, you also have the flip of the relation. So Peyton, what do you think? Is this thing symmetric? It is because the 1, 2, there is a 2, 1. What about the 2, 1? Flip it over, there's a 1, 2. What about 1, 1? Oh, it's there. Yeah. So this one is symmetric. Antisymmetric. This is weird. Well, no, it's not. This one's not weird. Antisymmetric means that if you have 1, 2, then you cannot have 2, 1. So this one is not antisymmetric. You might ask, can you have a symmetric and antisymmetric? Yes, you can, but we won't go over that right now. Maybe tomorrow or Friday, Wednesday. Transitive. Is this thing transitive? So I think we just mentioned it's not transitive because if you do 1, 2, and then you do 2, 1, you get the relation 1, 1, which is good. But what if you do 2, 1? 2 is related to 1 and 1 is related to 2, but 2 is not related to itself, so it's not transitive. All right, try the same thing. We only have 1 minute, but so we're not going to get down here, but I think we can do this really quick. So see if you can identify this. In fact, here we go. Sam, is this thing reflexive? So, yes, it is, because you have 1, 1, 2, 2, and 3, 3, all in my relation. So this thing is reflexive. Next, we're going to see, is it symmetric? So I guess we're over to John. Is this thing symmetric? Why not? Yeah, so you have a 1, 2, but no 2, 1. Very good. Symmetric is a no. Okay, what about antisymmetric? Antisymmetric is a yes. So just so you know, we'll just skip ahead because I want to get to transitive. Is this thing, what's that? So antisymmetric, the way you check antisymmetric is if you see a 1, 2, you better not see a 2, 1. Those don't count. So anything that's reflexive, you're okay. So 1, 3, you better not see a 3, 1, and you better not see a 2, 3, or 3, 2. Okay, transitive. What do you think, Lucas? Is this thing transitive?
I don't think so.
Okay, so if it's transitive, it means that if for example, 1 goes to 2, or if 1's related to 2, and 2 is related to 3, I better have a 1, 3. Okay, is there anything else we need to check? No, so this thing is transitive. Those 3. Do your best with the homework. We'll pick up the pieces on Wednesday, and we'll see you then. If you want, you can chat. Otherwise, I'm usually going to stop the recording since no one's going to watch it anyway, but just in case. Homework. Was there homework? Yes, there is.